Welcome all. It's nice that we're actually in a net zero church, so a net zero building. So this building actually kind of demonstrates a bunch of the principles that we're going to learn about today. So my name is Frank Crawford. I am a professional civil engineer. I am also a certified passive house designer. Before that, I had about a 10-15 year career as a commercial project manager, and including building a LEED Platinum and a LEED Silver or LEED Gold building. Left kind of the commercial world to design, build, and now I live in my family's passive house, which has a secondary suite in Calgary. And obviously we are here today to learn about passive house. This is kind of a general public introduction course to it. Okay, so here's the kind of brief agenda. So we'll start with an introduction, kind of why you pick passive house, the history of passive house, the benefits of passive house. After that, we'll kind of go through the 5 principles of passive house. It's kind of like the 5 main things. It's all the building science and physics, that how you actually get all the benefits and stuff that are listed before. So we'll go through some examples of passive house, the cost of passive house, always a big question, how it works well with other green buildings, and then kind of pulling it all together and kind of next steps and how to move forward. So I am with Passive House Alberta. We are a non-profit foundation. We're about 2 or 3 years old. Our vision is that Passive House is the standard for the built environment in Alberta, and it's accessible and affordable to all. So that's kind of why we're doing this education piece to help educate people on what Passive House is. I guess we're all here kind of today to talk about building, and why do we want to be talking about kind of different ways to be building? The reason is, so here's 2 pictures of houses. They're both actually from Calgary. They have a lot of things in common. There's 1 or 2 things that are different as well. So what they have in common is they could both have asphalt shingles. They could both have a stucco exterior. They're both probably either 2x4 or 2x6 stud, probably a poly vapor barrier, somewhat different siding, maybe single or double pane windows, but like architecturally they do kind of look pretty similar. The difference is one's from 1950 and one's from 2019. So like there's 70 years in between those buildings, and we haven't really learned anything, but we're not doing anything different. So if we continue to build like we did way back then, we'll kind of continue to get the performance of way back then. If you live in a kind of standard house, think to today when you woke up this morning. Was your furnace running basically constantly all night? Was it a lot colder in your basement than maybe your main floor and your upstairs? If you went near a window, was there ice and condensation all over that window? And if you went near the window, did you feel like a cold draft coming off the window? If you put your hand by an electrical plug on an exterior wall, do you feel a cold draft coming in? And also, is it noisy? And it's also probably kind of dusty or very dry air. So our houses don't really work in the winter. They're not comfortable. And if you kind of remember back to the summer, I don't know about Edmonton, but Calgary wasn't super warm. But if you think back to the really warm days, do you now want to go into the basement because it's cooler? Because the main floors may be comfortable, but your upstairs bedrooms or whatever, it's probably like 30 degrees and way too hot. So are you now trying to go to the basement to get cool? If it's smoky outside, like 2 or 3 years ago, we did have a fair amount of fires and smoke. Was it equally smoky inside? Is the house really better indoor air quality than the outdoors? Probably not. If you have air conditioning, is your air conditioning kind of running constantly to keep your house cool? So again, you have money and utility bills going out the windows all the time. And it's still noisy, still drafty, could still be dusty. We're told that our buildings are comfortable, but they're really not. When it comes to comfort, building code right now kind of fails us. They are safe. They've definitely had some great increases in safety, fire safety, electrical safety, all that other stuff. It won't fall down. It's structurally sound, but as far as comfort, indoor air quality, the code doesn't do us what we need. So, fortunately, there's another way to build, a better way to build, and it is the Passive House way. The Passive House way is kind of redefining safe and healthy buildings. So what is Passive House? What is the history of it? So if we go a very long time ago, in this picture, this is like hundreds of years ago, we kind of learned that if we're in a very hot climate, we don't want the sun coming into our buildings. So they kind of built this house in and under a cliff, so it's kind of in the shade most of the day, and it gets all the thermal mass of that rock, so it's not all that hot. So we kind of knew these are kind of passive solar principles. We kind of know these a long time. Kind of the first, what you might call passive house, was actually a ship. It was from 1897. So this is an Arctic exploration vessel. It's the Fram. So the Fram is a comfortable abode, whether the thermostat is 22 above or 22 below. We have no fire in the stove. The sides of the ship gave a total thickness of 15 inches. The ventilation is excellent, especially since we rigged up an air sail, which is just basically a sail that would help funnel more air down below, which sends a whole winter's cold through the ventilator. Yet, in spite of this, we sit here warm and comfortable with only a lamp burning. So that ship is kind of applying a bunch of these principles, whether or not they kind of knew about it. But again, that's from 1897. So we've been doing this for a while. Then kind of in the 1970s and 1980s, Canada actually became one of the leaders in passive solar design. And the reason is, at that time, there was the whole Arab energy embargo, and gas got 2 or 3 or 4 times more expensive than it was. And suddenly we're living in a cold climate. We need to burn fuel to keep us warm. If it got really expensive, then we got interested in, maybe we should worry about this energy efficiency thing so we don't have to pay as much money. So kind of passive solar came out of that, and the main principles of that were put a whole bunch of glass on the south side to collect all that sun's heat, and then a whole bunch of thermal mass inside the building to kind of store that heat, and then it kind of releases it later. There's some good starts, and actually we also developed the HOT 2000 software at that time, which was kind of a rudimentary energy model at that time. HOT 2000 is still around, it's been evolving, it's now a pretty good energy model. But yeah, in the 70s or 80s, we were kind of at the forefront of energy efficiency. But then the oil embargo ended, energy got cheap, and we forgot about it, or stopped caring. Just before we forgot about it, we did this. So Harold Orr, who is an engineer in Saskatchewan, they built the Saskatchewan Conservation House in 1977, so still the end of the oil embargo. And in that house, he kind of basically built one of the world's first heat recovery ventilators. He kind of designed some of the first triple paned windows. It is a deep double stud blown cellulose wall. They have large overhangs on the south side, so they're shading their windows in the summer. They're starting to apply pretty much all the principles that we will learn about later. So and actually Harold Orr just recently got kind of a Pioneer Award from the Passive House Institute for being one of the fellow founders of Passive House. But then in the 80s, we forgot about it, but the Germans didn't. The reasons the Germans didn't is the way their government worked. It was a proportional democracy, so the Green Party ended up being kind of the swing vote in a minority government. So in order to get their basically approval to prop up the government, the Green Party said, we want to do this, we want to look into energy efficiency. So the government started funding a whole bunch of research and pilot projects to look into energy efficiency of a building. And in the very technical, specific way that Germans seem to do things, they looked at kind of all the examples of passive solar and other energy efficient buildings all over the world. They looked at the Canadian examples and other examples. Then they did a whole bunch of projects, they did a whole bunch of research, they tested it, and eventually Wolfgang Feist and Bo Addison came up with the Passive House Energy Efficiency Standard. And the first Passive House was built in Darmstadt, Germany in 1991. So it's about now it's over 30 years old, standard, so it's not new. It was a fourplex, and Dr. Feist actually still lives in that same one of the units of the fourplex today. So obviously it's a comfortable house if he hasn't moved anywhere else in 25 years plus. Passive House today is now a worldwide standard. There's approximately 60,000 passive houses. That's about 2 years ago. And not all passive houses need to be certified, so that number is likely much larger. And it's a building standard in Europe, in Canada, in Australia, in Italy, in Brazil. Basically it works in every climate. All over the world, it's the same standard because it's just based on building science and physics with some hard prescriptive measures. And even more than this, so the city of Brussels in Belgium saw what Passive House was doing, and I think in about 2005, they decided that they wanted to make Passive House their building code minimum. which was a big step at that point. So they didn't do it overnight. I think they took about 10 years to do it. At the beginning, they funded more pilot projects. They funded more education of the construction industry, but they set out the plan that in 10 years, it's going to be code. So the construction industry couldn't fight it. They knew it was coming, but since they knew it was coming, they planned for it. They got educated. And then I think it was 2015 or so that it became code, and the prices didn't go skyrocketing through the roof like some people thought they would. There was a minor increase, but fairly quickly it kind of all evened out. So now everyone in Brussels that lives in a new house lives in a passive house. So it's not new. It's been around for a long time, and it can be building code. So coming back to Canada now, the first passive house in Canada was built for the 2010 Winter Olympics, and it was actually basically imported from Austria. So all of those materials were basically off-site fabricated in Austria. It's, I think, CLT, wood fiber board, brought over in a shipping container. It was Austria House during the Olympics, and then they just basically donated or left it here to help us learn about passive house. And it's still there. It's working pretty good. There's always a few tweaks when you move products from one climate to another, but it is working as it should. And so we've been back in the passive house game for about 10 years in Canada. So when Wolfgang Feist and Bo Adamson made passive house, basically what it needs to be is an energy model. That energy model is called the PHPP, or the Passive House Planning Package, and it's an Excel spreadsheet. So you don't actually have to learn any new software. It's just a very large Excel spreadsheet, and they're at version 9.6 now. So again, they don't stop. They keep testing, they keep evaluating, they keep updating as things change. It was based on the HOT 2000. HOT 2000 has been improving as well, but PHPP is a little more user-friendly and a little more detailed. Continuously updated, but it's still all got that building science in the background. So that's kind of the history of passive house. Now we'll go through some of the benefits of passive house, or why you would want to use this system. So the first benefit, and the most important one, because it solves all those other problems of a standard house, is you get comfort. Comfort in that there are no cold spots, there are no drafts, it is the same temperature basically throughout the house. Like your basement is the same temperature as your main floor, is the same temperature as your second floor, all through the year. So you don't have to avoid different spaces of the room at different parts of the year. You're comfortable all the time. And again, passive house, by the name house, you think it's just for residential. It does actually work for all types of buildings, including commercial buildings, including schools. So this is a quote from a passive house school in the US. "We feel that our children are more alert and more attentive in lessons due to the amount of daylight in the classroom and the fresh air throughout the school." So that's kind of a benefit of actually putting words and words to just kind of anecdotal, what does comfort really mean. This is my house. So that's a 5-foot by 10-foot triple pane window on the south side of my house. In front of that, that's actually our bench for our kitchen table. So it's minus 25 outside in that photo. And it's on a sunny day, it's one of the best seats in the house. It's very warm. My kids aren't always wearing pants, but it kind of shows how warm it is right beside a window. Like, would you want to do that in your kind of code minimum window? Probably not. So that's kind of what comfort should be. Inhabitants of energy efficiency, mechanically ventilated homes rated the quality of indoor air and climate significantly higher, and self-reported health improved more frequently in mechanically ventilated homes. So that's an interesting quote and comment, is that our health actually improved once we move into a more energy efficient, healthy home. Going a little bit further down that same health implications, mold and allergies. So allergies against pollen, pet hair, and insects are less frequently observed in occupants with mechanical ventilation. That's from a somewhat recent study. And we have known for a long time that the damp and mold will make asthma worse if you already have it. But this is one of the first studies to show that mold may actually be causing asthma to develop. So that was interesting. It's 3 years ago now, but it's interesting that maybe our current code minimum buildings are making us sick. because there does seem to be anecdotally a lot more asthma, a lot more allergies popping up now that weren't here maybe 50 years ago. So maybe it's our buildings. So a study also found that the more mold, the more cases of asthma. That kind of makes sense. And what is going to cause mold is if you have an area on the wall, on the exterior of the wall, that gets too cold, and some moisture gets on it, and then it condenses into water, and if it doesn't dry out quick enough, that's how you get mold. So by doing all these principles, you basically avoid that problem. And we'll do it more, when we get to the principles, we'll learn more how it does, but that's what it does do. So that's kind of comfort. You're going to have a comfortable house everywhere. The next benefit is you're going to have a quiet house. So obviously you have a lot more insulation, you have a lot more air tightness, your windows are higher performance and better sealed. That basically stops the sound from coming in. So again, this is in my house during a thunderstorm with my windows closed. The decibel rating was 30 to 40 decibels, which is a little bit more than a whisper. It's like a very slow or very light conversation. Most office buildings, I can't do it here because this is a passive house and it, again, is about 30 decibels. But everywhere else I've taught, the room I was teaching in, I used the same sound meter, which is just on my phone, and it was kind of 40 to 50 decibels with no one talking in the room. So this is during a thunderstorm. And then during the actual thunder clap, it got up to 45 decibels. Just to compare, I then opened the window and kind of put the meter kind of out the window, and it was 55 to 60 decibels outside and 75 decibels. So basically your passive house drops any outdoor sound down to pretty much not quite negligible, but definitely down into the talking range. And then if there isn't a thunderstorm, just the background sound, like when I go to bed in my bedroom, it's about 20 decibels, which is pretty much breathing. So there's no furnace fan that's running constantly. There is no mechanical background noise to keep you up. So if you live across from a train, like there is actually a train line 2 blocks away from us, when we're inside the house and the windows are closed, we don't hear the train. I know this because my 2-year-old and 4-year-old or 5-year-old, when we're outside playing and a train goes by, they run around going, train, train, because they like trains. So that's your non-quantitative reason for being passive house and quiet. But again, if you live under a flight path of planes, you wouldn't hear the planes as much. If you live right next to a busy street, that busy street now kind of becomes not busy. If you have lots of birds outside your window, you won't hear the birds in the morning. If you like hearing the birds in the window, open the window. But you've got that option now. So quiet is a benefit of a passive house. So here's a little movie from owners of another passive house. So you don't just have to believe me.
Not that we expected this, but this happened, is that it has had a pretty big impact on the quality of our lives here. Having a lot of access to natural light definitely has an impact on mood states and how we're doing mentally. Having the sunshine in and having bright light even on a rainy day like today is quite profound.
The other thing we really enjoy is just the quietness of the house. You can't hear a lot of the exterior stuff that you normally hear in a normal house. And then the last thing is the temperature fluctuations aren't as big, so it's much more comfortable and you're more connected to your environment.
In addition, I think I'll also add that just the noise from the interior running of a house, for example, the one thing we always notice when we come home from visiting others is the furnace or the air conditioner going on in the middle of the night in particular. Like even our kids feel like they're waking up at an airport in the middle of the night sometimes. So having that type of quiet and that reduction in noise pollution in the house is really profound.
Over the years that we've lived here, we've noticed that the air quality is significantly better than our older conventional house that we used to live in. So as an example, during the fires that were in Alberta last year, we closed all of our windows and everything else, and we're running the HRV at a relatively high rate to filter out all the ash and everything else that was in the air, and our air quality was significantly better inside than outside. The other thing is that you can turn the HRV down onto low in the summer, and it's really nice because you can open up a lot of the windows and get a lot of the fresh air inside of the house, and close them up during the nighttime, and the house reacts really well on good temperature in the morning.
The house is modeled in terms of heat and how it insulates that if it's a minus 30 day, it's minus 30 outside, it's 18 right at the window, and it's about 20 degrees in my space. And that's nice, that's great to know. However, from a functional perspective, when I live in it, if I was to close my eyes and I go from being at the wall to being at the window, back to the wall, I can't tell the difference. If I'm sitting at my dining room table, which is right in front of the window, I will never feel a draft. And that's the type of comfort that I really enjoy in this house, particularly because oftentimes we've been at other people's homes in the kitchen, same design, and you're uncomfortable, you need a blanket, you need a sweater because there's a constant draft traveling across your back. And so that's another one of those pieces that it seems so small, and yet it has a really significant impact on how you enjoy the space you live in.
Those are all the comfort, quiet, and kind of personal benefits. So the next one is the one that kind of everyone knows about, or anyone, it's kind of the first thing you know. So you do get energy savings. So with Passive House, you get kind of up either an 80 or a 90% reduction in the space heating and cooling demand compared to a code minimum house. So even compared to kind of a more high performance house, it might be 75% better, but you do get significant and tangible on your utility bill savings from building a passive house. So by reducing the amount of energy that you need, it to some degree you don't care as much about the price of that energy, because it could double in price and like, okay, I'm going to pay another $20 a month. Doesn't matter. Once you reduce that by 90%, if you used 90% more gas or electricity and the price doubled, you're paying like another $200 a month. So you still have kind of your fixed fees and you still have all your other stuff, but if the price of gas doubles, the price of electricity doubles, which it might, you never know, it's not as impactful on your kind of monthly budget. The other big benefit is because it's so airtight and it loses energy so slowly, if we had a grid problem and the power went out, like if the power went out today in your house, you would be phoning a plumber or a furnace person pretty quick, because you would probably be concerned that your house is going to freeze in not too long. And when it freezes, that's where pipes break and you get your waterfalls coming out of your house. In a passive house, because you lose energy so slowly, it could be 4 days, 7 days before you might be concerned about it getting below zero. And that's only if it's not cloudy. If the sun comes out at all during that time, your house will be fine. A passive house, if it's sunny, will not drop below zero, just because it's so well insulated. And if it sees the sun and allows the sun in correctly through the windows, the sun heats the house. So you can get 30 to 60% of your heat annually in the heating season from your windows. So passive house windows do cost more. One of the reasons they cost more is they're also a furnace. They are a heat source for your house, at least the south ones. So you're less concerned about a grid failure, and that kind of gives you building resilience or more safety. So the other thing about passive houses is basically you're spending a lot on your envelope, basically the jackets that you're putting on. So a long time ago in the 17th century, we lived in kind of tents or teepees. So if we were sitting by the fire and we had a big wood or big woolen coat on us, we were not dying. I'm not sure if we were ever comfortable, but we weren't dying. And then in the 19th century, we kind of maybe built stone houses or very rudimentary wood houses. And again, if you're standing beside the fire with a bunch of coats on, you're a little more comfortable, you're out of the weather. Kind of where we're a little bit stuck now in kind of the 20th century is the walls in the buildings haven't really got much better. There's a little bit of insulation, but not much. But we want the comfort. We don't want to have to wear a fur coat all the time. So in order to get that comfort, we need large, complicated mechanical systems. You need a big furnace, you need probably maybe some additional heaters, you need an air conditioner in the summer, you need a whole bunch of other expensive mechanical systems that need to be maintained, can break down, eventually need to be replaced. So it's just a lot of complexity to get some form of comfort. What Passive House provides is you have a much better envelope, much better air sealed, airtight. You let some heat in through the windows in the summer, so you need a much smaller, simpler mechanical system to meet your remaining heating needs and your ventilation needs. So when it's simpler, there's less moving parts, there's less things to break, there's less maintenance, it costs less. So another advantage is durability. So a passive house is designed to last 50 to 100 years with very little to no maintenance. You pick more durable materials, you protect them from degradation, and they last longer. Most buildings fail because of moisture. Where you have air leaving the house, you will generally have moisture leaving the house with that air. So these two photos, the first one is most likely the underside of a roof, and what you're seeing is the air tightness isn't there, so the moisture is going up, it's hitting that cold surface of the OSB, and it's condensing. And it's not drying out, so it's now growing mold and fungus and rotting away your roof or your supports. The picture below that is someone tried to be more energy efficient. He put, looks to be 4 inches of foam on top of a roof, but he didn't worry about the air tightness. So coming between all of those wood 2x4s is air and moisture. And then it hits that foam, can't go through the foam, condenses, gets stuck there, starts rotting out the whole building. So that's where you have to worry about durability. And just as an example, so that Wolfgang Feist's house, 25 years after he moved into it, he brought some people in and gently took parts of it apart. So they opened up a wall, looked at the wall to see if there was any degradation, if there was any water damage, and there was none. It was still just as good as when they built it 25 years ago. They did a new blower door test. The blower door test is how you test the air tightness. And once they replaced the bottom rubber seal on the door, it got the same air tightness as 25 years before. So nothing had changed. 25 years ago, there was very few triple pane windows. They kind of had to create one of the first triple pane windows. So again, it's a triple pane window with some gas in between the panes to give you the higher R value. So they weren't sure that that gas would stay, but again, they tested the windows and they all tested just as good as 25 years ago. They were a bit surprised on that, so they hadn't lost any gas out of the sealed units in the glass, so they now think that those windows, they lasted 25 years, they think they're probably going to last 40 or more years before you have to do anything. So again, the durability is there. So another way you can kind of visually see durability, this is a thermal imaging camera. And what it does is it sees the temperature of surfaces. Hot surfaces, which is what, this is done when it's colder outside than inside. So hot surfaces show you where heat and generally moisture is escaping from that building. So that circle there where it's reds and pinks and yellows, which is hotter, you would be concerned that there is probably going to be some damage, structural damage from moisture right at that location because there's a lot of heat escaping there. So the interesting thing is this, which is all blue, which means it's very cold. That's a passive house renovation. So it was the same kind of code minimum, not so good house. They did some renovation. They stuck some insulation on it. They did the air tightness. They put better windows. And now, if you look at the frame, it's that kind of green. So the frame of a passive house is always your worst performing spot, and it is about the same color as some of the old walls. So like windows are as good as old walls.